So can you hear me? No? Okay. So before starting, since I'm the last one in the session and in the workshop, I would like to thank all the organizers for setting up this program. I really enjoyed being here, and I think I'm not the only one who did. It was a nice opportunity. So my talk is a joint ongoing work with Serena Arima from the same department where I am in Sapienza in Rome. And I place myself at the very end of the protection process when the data have been perturbed and the user has to analyze the data. And I focus on random perturbation methods. And we have a sample which has been perturbed by random protection schemes. And as I said, I focus on ex post analysis. What happened? Okay. And we put ourselves in a measurement error scheme, and we assume that the final user has in mind a certain specific model, and he tries to adapt his inferences to allow for the measurement error or for the protection applied to the data. So we want to assess the effectiveness of such a strategy, and also the effect that such a strategy using an adapted model, what is the effect of this on the protection of the data in terms of attribute disclosure. So we consider two schemes. One is noise addition, and the other one is PRAM, which is a method to protect categorical variables. And we develop a Bayesian mixed effects model that incorporates the measurement error within the model and explicitly models the errors, the distribution induced by the protection on the variables. So we consider additive noise, normal, but of course it could be changed, and PRAM. So PRAM is a protection method developed in 1998 and draws from the literature about randomized responses, which we heard about some hours ago. And it works through the definition of a transition matrix, P, which is a k by k variable that depends on the number of categories of the variables that you want to protect. The variable you want to protect is x, and z is the released version of x. And PRAM is applied by perturbing each record attributes by applying the PRAM matrices, that is by drawing a value from a distribution which has masses pkh, where pkh is the probability of going from category k of the original variable to category h of the perturbed variable. And so PRAM is applied independently on each record in the file for all the categorical variables or for a set of categorical variables. And the same P is used usually, but there are several variants of this. We consider the very original scheme, and in the original definition, the matrix P has to be released in order to allow for correct inferences. One way to avoid to correct inference is by the definition and invariant version of the PRAM. So the idea is that if you have the distribution of your variable x, the one that has to be protected, you can define a matrix P such that when you back transform, in a sense, when you apply the Bayes theorem, P transpose times the contingency table observed for x, for the original variables, you get again the same empirical distribution, And if you apply this to the unknown distribution, the latent distribution that generates the data, this is also called the strongly invariant PRAM. So there are many possible definitions of invariant PRAM matrices, and one simple definition is through defining a given level of protection, which is defined through theta. Theta actually is the initial probability of not changing the category, and then you adapt to the observed frequencies this theta, this 1 minus theta if you want, by in such a way that you achieve invariance. So you have a diagonal matrix with theta value 1 minus theta value on the diagonal, and then you adapt this to the observed counts, and you don't get so far away from the original theta, but you adapt to have this invariance characteristic. So in order to allow for analytic validity, usually high values of the diagonal entries are chosen, so small values of this theta are suggested. But at the same time, this means that with high probability you don't change the values of the original variables, so you have to balance between these two aspects. The original idea is that randomness about whether or not the observed category has been perturbed, that is, corresponds to the original category, is sufficient to preserve confidentiality, which is questionable. So we cast this problem into a measurement error model, and we consider a very specific model actually, because we consider n records grouped into m different groups, each with n1 and m records, individuals inside. And we assume we have a response yij observed on the jth unit in the ith group, and this could also be perturbed. We assume this is a continuous response. Then we have Sij that comes from the original unobserved variable yij. It's derived from W by applying random noise, normal noise. And Zij come from Xij, the original values of the unobserved variable, by applying PRAM. And we assume that the number of categories for both X and Z are the same, is the same. Don't know. Okay, so our aim is to understand the effect of measurement error under this specific model that I'm going to present. So it's a mixed effects model that we assume that is of interest for the user. And also we want to assess the data, or besides the data utility, also the protection offered by PRAM in this specific context. We know that measurement error has effects on your inferences in the sense that it gives you bias in model parameter estimates, and also in loss of power in detecting the interesting what did I do? Interesting relations. Wow, interesting. What did happen? Well, that's unusual. Can you read it? Well. Don't know. Sorry about that. So there are other similar proposals. One regarding PRAM, especially, is by Sasha Slavkovich and Wu, a student of her, and they focus on log linear models. On Poisson regression and logistic regression, and in general, generalized linear models, whereas this second proposal focuses on mixed effects models, but only with continuous covariates subject to measurement error, and is a special version of small area model. So we consider categorical covariates, and we define a special I don't know, specialized model. Okay, which is, as I said, a mixed effects model where the response has two sources of variability. So the mean response has a regression structure depending on the categorical covariates, the indicator function of the categorical covariates, and continuous variables that can be observed without error or with error. And there is within group variation and between group variation. So this is, in the box, this is the model for the measurement error. So, as I already said, what we observe is a perturbation of the continuous variable with normal random noise, and the PRAMmed version of the original categorical variables. And since in the PRAM matrix, each row of the matrix which I didn't define, okay, each row of the transition matrix defines a distribution, so that is the probability of going from a category of X to each of the categories of Z. So over pk we place a Dirichlet distribution with fixed parameters, and we assume that these xij are uniformly a priori distributed. And then we have to specify all the model parameters priors. And we use vague priors and independent parameters. Okay, so as I said, originally the idea was to release P in order to correct your inferences when you apply, when you estimate some model. But the view of statistical agencies is that it's safer not to release P. And in circumstances like the one I am showing in the model we are considering, the data structure can be used to infer P together with all the other model parameters. So in practice, we can allow for both known and unknown transition matrices, and that's why we place the Dirichlet prior over the transition distribution pk dot.
The variance of the random noise that you're also adding to S or W?
No, this is also unknown. Can be estimated in the same fashion.
So you don't know P, but you're assuming it's drawn from some prior distribution?
Yeah.
So they should keep secret that prior distribution also?
Well, it's, I mean, enters the model, the user's model. So it could be anything. We use the Dirichlet, and it will affect your inferences, I guess, to a certain extent. But we use directly the units within each group as replicates to estimate p. So the aim of this study is to analyze the ability of our model to have useful inferences, and also to investigate the disclosure risk that is induced by using the model to make some attribute disclosure. And we investigate these aspects by a simulation study. So as far as disclosure risk is concerned, we consider the viewpoint of the statistical agency, but when a user is applying a model of this kind to the released data. So the idea is that if the user can incorporate the information provided by the data that are released through the model, it may infer the original categories of X. So if there is a link, a dependence between the response variable and the categorical variables or your covariates in general, you can do the reverse to infer to have an attribute disclosure, infer the values of X. So traditionally, the literature has focused on the so-called calibration probabilities, the posterior probabilities of the predictive probabilities of having a score H on the original values, given that you observe score K in the sample. So this is an inverse problem. And usually you focus on the diagonal values, I mean going from K to K. So if you observe K, what's the probability that the original value is also K? And you can, for instance, find the maximum of these probabilities over the set of unsafe cells, for instance, or unsafe categories or combinations K. But, I mean, this depends on whether you focus on, for instance, invariant PRAM, because otherwise you have to be careful about all the elements that I mean, sorry, I didn't state it correctly. So these, if you have an invariant PRAM, you can focus just only on the diagonal of the transition matrix, which has Z here and X here on the right. Okay, but in general, you have to use the distribution of the predictive distribution of X given Z. And given that we are estimating a model, so we can define the predictive probability given not only Z, but also the data and the model parameters, and we can integrate over the posterior distribution of our parameters given the data, our model parameters given the data. And so we obtain a predictive distribution that is the probability that X has a score K given all the information you have. So this is an analog of the calibration probability, but it also exploits the information conveyed by the model about the covariates and also incorporates the uncertainty about the model. It is record specific because you can score not only Zi in some sense. I mean, your score may be the same, but you have other covariates that may differ, so it's record specific. So different records may have different calibration probabilities. Unfortunately, it's also model specific, of course, so different users may derive different predictive distributions. And when you have more than a single variable, you can use the compounded version of these distributions. I mean, you can cross-classify all the variables, obtaining a single big variable with large number of categories. And you can apply PRAM to this and also define pi I star pi ij star in terms of this compound variable. And what should a user do? Try to estimate, try to infer x. So we work with the mode of this distribution, of the predictive distribution, and of course the mode can lead to a correct inference or incorrect inference, that is to a false discovery, a false attribute disclosure. So the agency should focus on the correct attribute disclosure, and so the agency should work conditionally on the true value of x, which they know, which the agency knows. So the idea is to estimate the expected number of correct re-identification for a user that uses the release the information together with the model and tries to infer x. And this number can be also converted into a true discovery rate for each category of x, or for the whole file we can consider the number of the rate of read identification in the file, for instance. As far as the utility, the analytical use of the data is concerned, again we restrict attention to the model that we are using, so it's very user specific, and we investigate the role of the model with measurement error in variables in obtaining useful inferences, so valid inferences. And we also investigate what happens when you neglect completely the measurement error, because we are using invariant PRAM. So we think that the agency releases data using invariant PRAM, and so in principle, since the contingency table cross-classifying the categorical variables is preserved, you might expect that inference could be preserved much better than in other schemes of PRAM. So we define a simulation study under which we consider measures of bias, MSE, and coverage for the estimators of the model parameters. So we generate from the model, we omit the continuous variable, we only consider categorical variables. So the covariates are categorical, dummy variables. And we generate a whole population from this model, which is a two-level model. We set a large variance between groups variance and a smaller within group variance. So the model is strong in a sense. And we set k equals to 3, so the covariate is a single categorical covariate with 3 categories. And we chose these values of beta. Then we increase k to see what's the effect on the inferences with these values of the coefficients. We omit the intercept. So after we generate the population, we PRAM the whole population, so we keep the perturbation fixed, and we draw samples from the population. The PRAM, as I said, is invariant, but we vary the diagonal values, so we vary the protection levels. Okay. So we compare 3 models, actually, to compare inferences. We use the proposed model, which is the one with measurement error incorporated. The gold model is the one that the agency can estimate because it uses the original values. And then we consider the naive model for a user that applies the same type of model but neglecting the measurement error. So this user, the naive user, has the same model, but pretending the covariates are not affected by error. So we focus on estimation of model parameters, and also on models' ability at reconstructing the original categories of X. We start with unknown P, and then we see what happens with unknown P. So we consider the posterior mean, the relative bias and MSE, and the coverage of credibility intervals averaged over the simulated data sets. The next slide consider 100 data sets generated from the population I showed you before. And this is the agency model, this is the proposed model, and this is the naive model. Sorry, I should start from here. So when P, the diagonal entries of the PRAM matrix is high, this means that the perturbation is low. So when perturbation is low, the proposed model in terms of bias, of MSE, and of coverage is reasonably good. It's comparable with the gold model that nobody else than the agency can estimate. Whereas the naive model has serious problems in estimating the variability, the variance component sigma square E, because you know the bias is incredibly high, and the coverage by consequence is very low, and it's low for many parameters in the regression. So it's not advisable, even if the perturbation is small, it's not advisable to behave as if no perturbation were applied. And if you increase the extent of protection, our model, the proposed model, seems to behave reasonably, except for sigma squared U, which has not so good coverage and has a high variability. But the naive model is really very, very bad. So in terms of analytical validity, when P is known, it's very bad to use the naive method to estimate the parameters. And our technique allows you to get the correct inferences. And assuming that you know P, we computed across simulation the percentages of correct inferences for the given category 1, 2, and 3, given the original scores. So this is a correct re-identification probability. And as you can see, for P equals to 0.6, which means that the probability of changing the value of X is quite high. Yeah, and under invariant PRAM, 0.6 should be the posterior probability of observing X equals 1, given that Z is equal 1, for instance. But in almost 99% of the cases, you get the right answer for the first category, and still it's very high compared to 0.6 when you consider the second and third category. I think this depends also on the values of beta we chose, because beta 1 is the highest. Not sure about this. But in any case, the rates of re-identification, in some sense, the probability of disclosure is very high, especially when the protection is assumed to be more effective, higher. So knowledge of P increases the risk of disclosure or attribute disclosure. When we increase K, so we get to 5 categories, the figures are similar. Of course, it's more difficult to infer correctly the values of X, and therefore even the performance of the model may vary a little bit, but still the proposed model is very reasonable in terms of coverage of variability and bias, relative bias and relative MSE. Both when P is small, that is the protection is high, and when P is high, that is the protection is low. Actually, maybe the gain is less so strong when you protect a little. But if you compare with the naive method, still you have big problems with the variance component, and the coverage is not very good. For instance, for P equals 0.8, beta 1 is not well captured, and so on. So unless the protection is very low, the naive model is not going to work. And about the measures of risk, you see still we have an increase in the probability of re-identification of attribute disclosure. Even when P is 0.6, you get up to 88%. So you should think about this. So PRAM seems not to be very effective. Now I show you some preliminary results when P is not known. For K equals 3, the same values as before. And here the model performs not so well for some parameters, but even under the gold model, the coverage is not so good. I mean, here I did only a few replications, only 30 instead of 100, so maybe these are not so stable, these values here. But the coverage of the naive method is awful. So unless, as I said before, unless the protection is very mild, the naive model doesn't work very well in terms of coverage and MSE, whereas the proposed model still is quite reasonable. So analytic validity is preserved. As far as protection, the same story. Using the model to infer P and then X helps you a lot in recovering the correct inferences. So even if P is not released, you can have an advantage by estimating a model and trying to infer the categories, the original categories. Now we consider also a different instance, because before we generated the values of X from a uniform distribution, whereas usually you protect because you have rare categories. So we generated from a population in which a category, the fifth, has a very low probability of occurring in the population. And in that case, using the model, we saw that this category has a probability 0.93 to be recovered, even though using invariant PRAM, the diagonal term is 0.6. And so the posterior probability without using the model should be 0.6 of correct way identifying the category. And the model, I only use 0.9 because still we are working at that. The model works fine, but in the rare category, which has a high variability and low coverage, and also beta 4 is not very well estimated. So in this case, it's more difficult because the category is rare and the model works less well, of course, because we don't have occurrences of this. But yeah, we still have to work at that. So to conclude the talk, we only focused on invariant PRAM and focused on a user willing to estimate a specific model. We view this from the point of view of the agency, and evaluated the analytic validity of a specific model and of ignoring the protection at all for this specific model. And we consider also the effect in terms of protection of applying PRAM. And of course, the extent to which the proposed model corrects the inferences varies with the level of perturbation, but in general is good. It also varies with the number of categories, I guess. This is still to be checked, but I expect this is the case. The important point to me is that the model can be used to infer the original categories of the categorical variables x, and releasing p is risky indeed. And you can design a model in such a way that you can estimate p. So sometimes you have the model, but sometimes you can just build a specific model just to estimate p, I think. So the model structure could be employed just for the sake of estimating p and inferring x. For instance, this morning we saw some application about credit scoring, and there are demographic variables, and you could use these together with loan values and so on. So this could be an application. And you could use a model just for, not because it's of your inferential interest, but just because you want to estimate p. So this is still ongoing work. If you have suggestions, these are welcome. And of course, we have to investigate what happens when k increases, and this is the case when you have multivariate PRAM. And as far as disclosure risk is concerned, I think that using the model, the information that the model conveys about x is important. And this gives record-specific measure, but also model-specific, which is not so good. I don't know, maybe you can model average, but I think it's not going to be very practical. So we consider somehow new measure of risk, which is the proportion of true categories that are correctly inferred from the released data. And I think that's it. Thank you very much.
Questions? Natalie?
I have two, but first I wanted to ask, the first one is, you did PRAM on the population, and then you drew samples. So, and generally what you would have is a population draw samples, and then on each sample you do the PRAM, because it's a post, it's done after. So it seems that you're only capturing sort of sampling error here instead of sort of the perturbation error, or?
Actually, we did on purpose because we thought that repeating the application of PRAM would induce extra variability, and so you mixed things, I guess. Because since we are Bayesian, we consider the data as given, and if we change across simulations the perturbation structure, I think this would mix things, sources of variation, I guess.
And my second question is, you've used in very simple PRAM matrices where you had a fixed diagonal, fixed off diagonal, and so would you be able to recover so well if you just had a general perturbation matrix where the off diagonals were not all equal?
Yeah, we have to investigate this. Actually, yeah, you mean invariant anyway.
Yeah,
also invariant, but more
not necessarily fixing the off diagonals to be all the same.
Mm-hmm. Yeah, it helps in the reconstruction probably. Even the generating the data from a uniform distribution is not so fair. So we change it.
Yes, very nice presentation. I was curious about what you mean by a strong model. I think it was one of your last slides. And also, if you could say something about that, but also I haven't quite got the intuition of how you actually get back these PRAM parameters. Where does the information come from? Natalie's question was helpful, but it seems a really hard thing to do.
Well, so the strong strength of the model comes from the sigma square u, because of course this is the regression. If the regression is weak.
Oh, you mean a regression with strong predictors?
Yeah.
Oh, good, I understand that then. Yes, I thought it was something else.
The extra variability around the regression given by sigma square u here.
Yeah. Where does the information come from, so you can find out what
If you have a link between x and y to the mean value here, of course, since it's a Bayesian model, you can invert the relation and get the distribution of x given all the rest.
Mm. And so it's the fixed pattern that's giving you this to come out, so I can see how it wouldn't work so well. Yes, I see what you mean.
Yeah, if the model it's reasonable and it has a good fit, I expect that the relation between yij and my covariates allows me to understand what are the covariates.
Thanks, that's good.
Can I ask a question? I think your last bullet point on slide 31 said the results might change if you change the number of categories.
Mm-hmm.
What about if you change the number of observations? Because all your tables have 5 to 17 observations. And you mentioned credit score, and you're going to have a lot more.
Yeah, of course, if you have more observation, this helps, especially when you have to estimate p. But since we started thinking about this within a small area context, we chose to have a little number of units within each group.
Are there any other questions? If not, can we thank Silvia once again for a great presentation?